So let us now turn to a more detailed analysis of the Airy's equation. So the equation itself, again, looks very simple. And as we have just discussed, its wave-like nature allows for some approximate solutions. And before dealing with approximate solution, let us concentrate on what we are looking for. As a wave-like equation, we expect it to have the solution with the following sketchy properties. So this is the solution which we are going to look for. And in fact, this particular solution is very well known, and it's called Airy's function. And one of its representations is in terms of the following integral. The integral which we choose to work with for now is running over the real axis. And allows to evaluate this function at arbitrary z. And what is useful in this integral is that it allows to quickly check and convince ourselves that this is indeed, first of all, a solution of this equation, and second, a solution with proper asymptotic behavior at large positive z. The first part is done in spirit of the Laplace method, which is familiar to you by now, so let us leave it as an exercise. And the second part amounts on evaluation of this integral by a saddle point method. This is again relatively straightforward, and let me give you a result of such a calculation. So at z, which is large and positive, the asymptotic is and this is of course valid in the asymptotic sense. So the derivation of both these facts, first of all, that this integral does satisfy this equation, and that the asymptote of this integral does indeed behave exponentially at large z, is left for you as a homework exercise. And for now, let's take it for granted. So for the moment, let us turn back to this equation. Again, as we have mentioned, its wave-like nature allows to guess that there should be two functions which are almost solutions, and they are not exactly solutions as can be checked almost immediately, but almost solutions of the following form. The derivation of the fact that they are almost solutions is standard for most quantum mechanics books. But let us now look closer and in which sense does this function represent an approximate solution. And then we will try to connect this set of linearly independent solutions with an exact expression for Airy function. So the first step in this direction would be the following procedure. Before giving you the details of this procedure, let me recall you what we actually have achieved in one of the previous homework exercises. We did construct the solution of this equation in terms of some powers, of some positive powers of the variable z. And this series did give a representation for two linearly independent solutions, which were given by convergence series and hence well defined for arbitrary z. In fact, an interesting procedure would be to look for a solution of this equation in terms of the series over negative powers of z. And in fact, this happens to be possible. And with the proof delegated to your homework, let me give you the result, which I will now use. And it reads as follows. Quite a general statement can be done, which tells that the following series, which is only formal but still can be quite useful, does indeed solve this equation, not approximately, but to some extent exactly. Before clarifying on the meaning of these words, let me write down the series explicitly. So this series, if treated formally, can be substituted to the Airy's differential equation, and again, term by term, one can check that all of the terms in this equation do indeed vanish. However, this series has an important flaw, and in fact, this flaw is by now quite familiar to us, and this flaw is the fact that this series does diverge. So in certain sense, although it formally exists and satisfies the Airy's equation, it doesn't define function y of z in pure mathematical sense. So this is obviously a problem, but however, let us treat this set of solutions as a fundamental one with drawbacks which we will see momentarily. So as a first application of these two sets of linearly independent solution, we may notice that according to the asymptotic, so again a of z, the function which is defined by this integral, is asymptotically equal to 1/2 square root of pi. And in fact, if we inspect this series, we see that its zero order term is nothing but 1. So in fact, it is interesting that this factor turns exactly to the leading term of the asymptotics, which can be obtained by a saddle point method applied to this integral. And interestingly, what we arrive to is that, in fact, Airy function is nothing but one of these two linearly independent solutions. And it seems that we can actually even find the coefficient in front of this solution. But already at this stage, we realize that what are the drawbacks of this representation, which is based on divergent series. And the drawback is the following. Imagine for a moment that we have managed to expand this Airy function as a linear combination of two convergent series, both of which are solutions. Then we realize that if we manage to write something like this, which is expansion over two convergent series solutions, then we may read this expression literally in a sense that this C1 and C2 are indeed constants. Suppose now we want to interpret this approximate equality as literally as this one. Then we see that immediately we come to a problem, because this function y2 of z being continued to the negative axis of z can never lead us to a real solution. From the very beginning, we see that this function y2, represented by the series, which first term of which is here, is already complex. So this paradox, treated seriously, will lead us in the end to full and deep understanding of the Stokes phenomena. But at the moment, let us notice that the literal reading of this equality is impossible, and what we need to understand is to which extent this coefficient here is indeed constant.